Hi students, let's solve the first problem from exercise 1.1. Determine whether each of the following are reflexive, symmetric and transitive. You have set A which goes from 1, 2, 3, 4, 12, 13, 14. So there are 14 numbers in set A. And what is the relation? R is equal to R as ordered pairs x and y, where 3x minus y is 0. This means R is equal to xy. I know x. I can take x from this set A. What will be y? Y is given by this particular equation. So what does this mean? Y is equal to minus y is equal to 0 minus 3x. Therefore, y is equal to 3x. So this is the value of y. Basically, y is 3 times of x. So y is equal to 3 times of x. So now let me first form a relation. Let me get all the ordered pairs in the relation, right? To figure out if it's reflexive, symmetric or transitive, I should first have the ordered pairs in the relation, right? Let me form the relation. So I'll take the first element 1. Y should be 3 times of x. So if x is 1, y should be 3 times of x. That is x is 1. So it's 3, right? 1 comma 3. X is 1 and y is 3 times of x, 3 into x. So if x is 1, y is equal to 3 into 1, which is 3. So 1 comma 3. Now next one would be, I'll take x as 2. If x is 2, then y is 3 times of x, that is 6. Next I'll take x as 3. So y will be 3 times of x, 3 times of 3, which is 9. Similarly 4. 3 times of 4 is 12. Now I'll take the fifth element 5. 3 times of 5 is 15. Now carefully observe, is 15 part of this particular set A? No. So you should always get the ordered pairs in such a way that both the elements x and y belong to set A. So here if you see, 15 does not belong to the set, right? 15 does not belong to the set. So this is not a valid ordered pair. The set ends here. The set ends here. Because if you continue, you will not get the elements. So if I take 6, 3 times of 6 is 18. 18 is still not present in this. If I take 7, 3 times of 7 is 21. 21 is not present in this, right? So we'll stop it here. Now we have the relation. Let's find out if it's reflexive. So if it has to be reflexive, what is the condition? A comma A should belong to relation R. A comma A should belong to relation. For every, this is for all or every element that belongs to set A, right? So set A is given here. For every element of this set A, you should have A comma A, right? So if I take 1 here, set A as 1 here, do I have 1 comma 1 here? Do I have 1 comma 1? No. 2 comma 2? No. So therefore this is not reflexive. Now we'll go through second type of relation, that is symmetric. Is it symmetric? What is the condition for symmetric? If A comma B belongs to R, this implies that B comma A should also belong to R. So now let's look at the ordered pairs in relation. You have 1 comma 3. If 1 comma 3 is there, then you should have the reverse combination, which is 3 comma 1. Is 3 comma 1 there? No. Since 3 comma 1 is not there, this is not symmetric. Now we'll check if this is transitive, right? We will check if this relation is transitive. What is the condition? If A comma B belongs to R and B comma C belongs to R, then A comma C should also belong to R, right? If this condition is satisfied, then you can call it as transitive. You take the first ordered pair, 1, 3. If you look at the common element, the second element you should have some common element here. Here you have 3. Now, 1, 3, 3, 9 means you should have 1, 9. Right? Second element here and first element here is same. So, first and fourth element should be present. First and fourth element. First element and fourth element. That is 1, 9. 1, 9 should be present. Is it present here? No. Therefore, this is not transitive. Not transitive. So, the way you should write the answer is, for reflexive, you can say 1, 1, 2, 2, 3, 3 are not present in R. Therefore, R is not reflexive. This is one way of writing. The other way of writing is A does not belong to R for all A belonging to set A. This is another way of writing. Therefore, R is not reflexive. Right? You can either write it this way or this way. Now, for symmetric, how will you write? You will write AB belongs to R implies that BA belongs to R. Right? But here, BA does not belong to R. So, it does not imply. Right? AB belongs to R does not imply that BA belongs to R. Right? This example. 1, 3 belongs to R. You can write example. 1, 3 belongs to R, but 3, 1 does not belong to R. Therefore, R is not symmetric. So, you can either write it like this or you can write it with an example, making it more clear. Now, for transitive, how do you write? You can write it like this. AB belongs to R, BC belongs to R, but AC does not belong to R. So, example, 1, 3 belongs to R, 3, 9 belongs to R, but 1, 9 does not belong to R. This symbol indicates does not belong to R. Therefore, R is not transitive. Now, let's take the second example. Relation R in the set N of natural numbers defined as y is equal to x plus y and x less than 4. Now, the set is N and this set of natural numbers. What is natural numbers? Numbers starting from 1 goes till infinity. Right? That is all positive numbers. Only positive numbers starting 1 till infinity is natural numbers. It does not have 0. Okay? It does not have 0 because 0 is not a natural number. It does not have 0 in this. Okay? So, now this is the set. Now, what is the relation given here? Relation is you have ordered pair xy where x is less than 4 and y is equal to x plus 5. So, this is the relation. Now, let's first form relation with some ordered pairs. Let's first find that. So, R is equal to x is less than 4. So, I can take 1, 2, 3. Right? I can take set with 1, 2 and 3. It cannot be equal to 4 or it can't be greater than 4. It should always be less than 4. So now you have 3 ordered pairs basically. Now we need to find the second element. What is the second element? It's given by this equation x plus 5. So you add 5 to the x. So you add 5 to x. So 5 plus 1 is 6, 5 plus 2 is 7, 5 plus 3 is 8. So this is the relation. Now we'll have to find out if this is reflexive, symmetric and transitive. So first one is reflexive. So what is the condition for reflexive? For every element A belonging to set n, in this case it's this set n, A comma A should belong to R. This is the condition for reflexive. For every element that belongs to natural numbers, A comma A should belong to R. Now here you have 1. So you should have 1 comma 1. Do we have 1 comma 1 here? No. Right? 1 comma 1 is not there. So 1 comma 1 does not belong to R. Right? Therefore, you can say A comma A does not belong to R, and therefore R is not reflexive. R is not reflexive. You don't have 1 comma 1, 2 comma 2, 3 comma 3. Therefore R is not reflexive. Now we'll figure out symmetric. Now what is the condition for symmetric? If AB belongs to R, this should imply that B comma A also belongs to R. That is, the reverse combination should be there in R. Now let's go and check out. We have 1 comma 6. We don't have 6 comma 1. We have 2 comma 7. We don't have 7 comma 2. The reverse combination is not there. Right? The reverse combination is not there. Therefore, you can say example, 1 comma 6 belongs to R, but 6 comma 1 does not belong to R. Therefore, R is not symmetric. Or you can also write, since AB belongs to R and BA does not belong to R, AB belongs to R, but BA does not belong to R, you can say R is not symmetric. The next one is transitive. What is the condition for transitive? If A comma B belongs to R and B comma C belongs to R, then it implies that first element and fourth element, that is A comma C, belongs to R. Now we should check if this condition is applicable. So A comma B belongs to R. So you have only these three ordered pairs, 1 comma 6, 2 comma 7 and 3 comma 8. If you notice, the second element 6 here, right? But you don't have any ordered pair with starting with 6. And here also second element is 7. You don't have any ordered pair starting with 7. So you cannot validate at all, right? This B comma C does not exist in R. B comma C does not exist in R. Therefore, you will not call it not transitive. You will say it is transitive. Therefore, it is transitive because you cannot validate. You cannot figure out. Since you cannot figure out, you cannot conclude that this is not transitive. So you will say this is transitive because you cannot verify. Because B comma C is not there at all in that list. Therefore, since you cannot verify, you should write A comma B belongs to R, but B comma C does not belong to R. Therefore, R is transitive. This is very important. Because B comma C does not belong to R, that is, you don't have 6 comma something or 7 comma something or 8 comma something. Since this does not exist, you say R is transitive. Now, I'll modify this slightly. I'll just modify this slightly. Instead of 2, say I have 6 comma 7. Just for example, say I have 6 comma 7. Now I can validate because 1 comma 6 is there, 6 comma 7 is there. Now based on transitive, what should I have? I should have 1 comma 7. I should have 1 comma 7 here. So since I have 1 comma 6 and 6 comma 7, I should have 1 comma 7. That is the first element, and the fourth element should be there in the ordered pair. But 1 comma 7 is not there. So in this case I would call it as not transitive. In this case I'll call it as not transitive. So I hope this difference is clear, right? I hope this difference is clear. So let's take another example. Relation R in the set A has 1, 2, 3, 4, 5, 6, and the relation is y is divisible by x, right? So you have a set with elements from 1 to 6, then the relation is defined as y is divisible by x. So basically R has all ordered pairs where y, that is second element, is divisible by first element. So for example, you can say 4 is divisible by 2, and 4 and 2 both should belong to A, right? Set A. The elements, the second element and the first element should belong to set A. Now let's first figure out if it's reflexive. So what does reflexive state? It states that for every element A belonging to A, that for every element in this set A should be divisible by A. That means here y is divisible by x. Y is second element, but in reflexive case, second element and first element should be same thing, right? So that means x and x. That means x is divisible by x, right? Or A is divisible by A. Now here I can consider first element, say 1. Is 1 divisible by 1? Yes, right? 1 is divisible by 1. 1 by 1 is 1. Similarly, I'll take number, second element 2. Is 2 divisible by 2? 2 by 2, it's divisible, right? Then is 3 divisible by 3? Yes, 3 is divisible by 3. So that way, every element is divisible by itself, right? So you can say, since for all A that belongs to A comma A belongs to R. That is nothing but, you can also say, for every element A that belongs to A, you can write it as x because they've given x here. They've given in terms of xy, so we'll put x. For every element x belonging to set A, x is divisible by x. Therefore, R is reflexive because x is divisible by x. Second element is divisible by the first element. In this case, both are same for reflexive. Now let's take symmetric. What is the condition? For every pair A comma B that belongs to R, B comma A should also belong to R. This is the condition, right? So now we will see. We'll go back to relation. Relation is y is divisible by x, right? Now, for example, if I take 4 is divisible by 2. 4 and 2 are present in this set A. So I'll take 4 and 2. 4 is divisible by 2. Does that mean for symmetric it should be reversed? 2 is divisible by 4. Right? If 4 is divisible by 2, does it mean that 2 is divisible by 4? No. Right? Because I can say 4 is divisible by 2. Right? But 2 is not divisible by 4. This will become half. It will become 0.5. Right? And here you get 2. You get the whole number as the answer. But here you get in decimal. This means that it is not divisible. It's not divisible. So whenever you get a decimal point, it means it's not divisible. Right? Simple. So here if you take 4 divisible by 2, you get the answer as 2. But here if you take 2 divisible by 4, you will get 0.5, which is a decimal. And that's why it's not divisible. I'll take this an example. 4 is divisible by 2, but 2 is not divisible by 4. 2 is not divisible by 4. Hence, R is not symmetric. Right? How should I write? I can also write it as, for every pair AB belonging to R, BA does not belong to R. Or I can say XY belongs to R, but YX does not belong to R. Therefore, R is not symmetric. You can write it this way also. So you can take an example and say that R is not symmetric, or you can write in this format. XY belongs to R, but YX does not belong to R. Hence, R is not symmetric. See, this way also you can write. Y is divisible by X, but X is not divisible by Y. Hence, R is not symmetric. You can write it this way also. Right? Now let's look at transitive. Right? What is the condition for transitive? If XY belongs to R and YZ belongs to R, then first and fourth element, that is XZ, should belong to R. This is when it is transitive. Now here, what is the relation? Y is divisible by X. So, what should I say? Y is divisible by X. That's what they've told. Y is divisible by X. That's a relation. If Y is divisible by X and Z is divisible by Y, look at this. Look at this statement. If Y is divisible by X and Z is divisible by Y, then X is divisible by Z. Now what is the relation here? Relation is Y is divisible by X. If Y is divisible by X and what is the second case? Z is divisible by X. And if Z is divisible by Y, then what is this combination? X comma Z. Then Z is divisible by X. So here you have, in this case, first one, Y is divisible by X. Second one, Z is divisible by Y. Z is divisible by Y. Therefore, Z is divisible by X. Now, let's take an example. So, let's take X as 4. So, can I say 4 is divisible by 2? That is 4 by 2? Yes, 4 by 2 is 2. It's a whole number. It's a whole number. That means it is divisible. 4 is divisible by 2. Now, next one is, we need to find out Z. Let's say Z is equal to 8. Then 8 should be divisible by Y. What is Y? 4. Is 8 divisible by 4? Yes, right? 8 divided by 4 is equal to 2. Again, it's a whole number. Therefore, it is divisible. Now, second condition is satisfied. Let's look at third condition. Z is divisible by X. What is Z here? 8. 8 divisible by 8 should be divisible by X. That is 2. Right? That is 2. 8 is divisible by 2. 8 by 2 is 4. It's a whole number. Therefore, it is divisible. So, using this example, we can say that R is transitive. Right? Using this example, we can say R is transitive, or we can say, since Y is divisible by X and Z is divisible by Y, Z is divisible by X. Therefore, R is transitive. Or you can simply say x comma y belongs to R, y comma z belongs to R, therefore x comma z belongs to R. Therefore R is transitive. You can simply write this particular statement. So here in this particular example, R is reflexive, R is not symmetric, but R is transitive. So you should write R is reflexive, transitive, but not symmetric. Now let's take this particular example. Relation R in the set Z. Z is set of all integers. Integers are numbers from 0 to infinity. It can have both plus and minus, right? Both positive and negative numbers. Plus 1, minus 1, plus 2, minus 2, plus 3, minus 3. But it will not have decimal numbers. It will be whole numbers, right? Integers are always whole numbers, right? They don't have decimal in them. They don't have decimals, right? So that's what is integer. Now you have Z, which is a set of all integers. The relation given is x minus y is an integer. X minus y is an integer. Now let's look at reflexive condition. For reflexive, both first element and second element has to be same. So here x minus y, we have x minus y is an integer. This is the relation, right? So instead of y, I'll put x itself, right? Instead of y, I'll put x itself. So x minus x is an integer. Is this true? X minus x is equal to 0, right? X minus x is 0 and 0 is part of the set Z. 0 belongs to Z. Therefore, this is reflexive. So you should say x minus x is equal to 0 and this belongs to Z. Therefore, R is reflexive. So now let's look at symmetric condition. For symmetric, if x minus y belongs to R, then y minus x, that is reverse it, right? Y minus x should belong to R and it should also belong to integer, right? Whatever answer you get out of this equation, it should belong to this set of integers. So let's take an example. If I take x as 2 and y as 3, so it will become 2 minus 3. 2 minus 3 is minus 1. Minus 1 belongs to Z, right? Minus 1 belongs to Z. Now I'll swap it, right? Instead of x I'll put y and instead of y I'll put x. So 3 minus 2. So 3 minus 2 is 1. Again 1 also belongs to Z, right? So therefore R is symmetric. So how do I write it? X minus y belongs to R implies that y minus x also belongs to R. Therefore R is symmetric. Or I can say x minus y is an integer. This implies that y minus x is also an integer. That is the relation here. Relation is x minus y should be an integer. So x minus y is an integer. Y minus x is also an integer. Therefore R is symmetric. Now let's look at transitive case. So for transitive case, we should have a combination like this. If x and y belongs to R and y and z belongs to R, then first and fourth element, that is x comma z should belong to R. Then we say R is transitive. Now here let's take this xy, yz, zx combination. So what is the relation? X minus y should belong to z. Now if x minus y belong to z, then I'll take yz combination. Then y minus z belongs to z, which implies that first element x and last element z. X minus z belongs to z. This is true, right? Now let's take an example and figure out. If I take x as 2 and y as 3, right? X as 2 and y as 3, I'll get 2 minus 3 is equal to minus 1, which belongs to z. Now next is yz combination. This is x, this is y. So I'll take y and z as 4. So 3 minus 4 is minus 1. Now what should happen? XZ combination, right? X is 2 and Z is 4. X is 2, right? X is 2 and Z is 4, right? So 2 minus 4 is minus 2, which belongs to Z. So now if you take an example also, you can prove that the relation is true. All these three are true, right? Therefore, you can say R is transitive. You can write it in this format, or you can put this example and say, since x minus y belongs to z and y minus z belongs to z, can imply that x minus z belongs to z. Therefore, R is transitive, right? You can also take this example and say, since 2 minus 3 belongs to z and 3 minus 4 belongs to z, therefore 2 minus 4 also belongs to z. Therefore, R is transitive. Now, this is an equivalence relation. Why? In this case, we saw that R is reflexive, R is symmetric, and R is also transitive. Since R is reflexive, symmetric, and transitive, we can call this an equivalence relation. We will solve the fifth part in the next video. If you have liked this video, do press a like and share it. Thank you.